shock, and gradually, like, we can get like how much is the movement for the motor using the potentiometer that we have. And in the component level, the robot was designed in a pretty modular way, so we had several of the components which were interchangeable, which is beneficial for manufacturing and assembly both. And Modred 2's body was designed in such a way so that we had some specific segments for the robot module. So this was similar for the early version as well, but here we tried to solve the accessibility of different components as well. And so we, each of the segments, like especially the larger segments, we actually designed in such a way so that they're in 3 different segments. In that way you can easily maintain the parts inside. So compared to Modred 1, in Modred 2 we have, of course, enhanced sensory capability and computation capability. So in Modred 1 we used Arduino microcontroller, but in Modred 2 we are using BeagleBone single board computer. It's comparable to, say, a Pentium 2 computer, so it's very powerful, and it has the inputs and output pins, so it's made for embedded systems pretty much. And we have some other sensors like infrared sensors, even small cameras we're planning to put, and XB radio for the radio communication between the modules. Now, these are the contributions made by the Modred and Modred 2 systems. We made one 4 degree of freedom robot, which has like a chain type robot using the Modred 1, and Modred 2 is a hybrid type of robot. You'll see the difference in the next chapter when we discuss about the gates. And of course, Modred 2 is more designed for the unstructured or rough terrain traversal, which was our goal. Now we have these 2 robots, and we want to explore more towards the docking mechanism of the robot. So say you have a lot of this type of robots in Mars or say Moon, and then some of them are connected together, and say 3 of them are connected together and 1 of them is not working. So if they cannot disconnect from that non-functional module, then the overall system fails, which is explained in the picture on the top. To solve that problem, we designed a new type of docking mechanism, and this is single-sided docking or undocking capable. So if the robot is single-sided docking capable, then if 2 of them are connected together, say this is not working, then the other one can disconnect, deciding by its own. In that way, the whole system survives. I'll just pass around this one. So the idea was we use some carved contour locking fingers, which actually rotate to attach with each other. And the carved contour was given for allowing some self-alignment and fault tolerance in the system. As you can see in the video. So it's showing some of the main parts of the docking mechanism. There's some alignment pegs in the corners as well. You can rotate in both the directions. So we attach one robot with it which has one part because it has limited capacity to lift load. So it works. And say now if this robot is not working, then the other one can actually detach from it. You can see that here as well. So even in twist, it works the same way pretty much. And for Moderate 2, we actually just improved the design, and then we improved some of the wiring issues that we had in the previous one. So these are the pictures showing that. And using Moderate 2, how actually we're gonna use the self-healing technique is shown in this one as well. Anybody has any questions so far? We can then move to the gates development using the moderate robots. So in the nature, actually, if our robot wants to learn how to walk, in the nature we have a lot of examples. We have some great teachers. And all of them are doing great in traversing over different types of obstacles and different types of terrain types and so on. So just think that if one robot can actually get all those configurations, how it would be. It's like you have a robot in this type of pebble type of terrain, it can become a spider and it can move around. And then when you see an obstacle, maybe the spider is not working well there, then you just reconfigure into an inchworm and then move over the obstacle and so on. So we had a lot of bio-inspired gates that we developed. These are some of the gates that we already demonstrated and also proposed. And some of them are wheel type of locomotion, and some of them are like worm type of locomotion. And this is the 2-module locomotion using gate using 2 of the robots connected together. So using the same robot, we could get different types of gates. This is the inchworm gate. So 2 of the robots are connected together and they're trying to be an inchworm. It's struggling to go forwards and very slowly. And of course on table, like lab table, so we have to gradually make it move on rough terrains eventually. Which is very much possible using Moderate 2, the second version. Okay, it's tired. And using the same robot, we can get wheel locomotion, like twisting, pivoting. Or moving like a 2-wheeled vehicle. Again, twisting, and so on. So for Moderate 2, we can get actually many more locomotion gates and many more configurations because of the 2 docking mechanisms connected from the side. And only using few robot modules, like we can get these many, this is just a very few examples. Actually, we can get a lot more configurations using Moderate 2. Like you have quadruped, scorpion-like in B, and then platform lift in C. Also, D is a 4-wheeler vehicle type of motion. E is a hexaped, and in F it's a combination of leg and wheels. So if you increase the number of modules, then we can get even more complex and amazing gates. Like in A, like snakes. Or if you want to make it more stable, like B is a double snake, or C is even like humanoid. So only using 11 robot modules, you can get a humanoid robot. So using Moderate 1 and Moderate 2, we could actually, we proposed and we demonstrated several gates, locomotion gates, and we need those locomotion gates for the robots to survive successfully in the rough terrain environments. Okay, now we know how to walk, but we have obstacles in front of us. So we have to learn, or we have to use techniques to avoid the obstacles. So we simulated that Mars environment like this. Not a bad approximation. Okay, we have flat terrain, but we have some obstacles, and we have some robot agents that carry some payload. So this is based on multi-agent systems, and here there are robot agents and payload agents which actuate on the environment, which is the terrain or obstacles, and they perceive from